Mass creates gravity. Everybody knows this. You learn it when you are 10 years old. The Earth has mass. The Earth pulls things down. The Moon has mass. The Earth pulls the Moon. The Sun has mass. The Sun pulls the Earth. Mass makes gravity. Gravity is a force. Simple. Done. And I am telling you right now, flatly, without any wiggle room, that this picture is completely wrong. Not a little wrong. Not wrong in the details, but right in spirit. It is wrong in a way that once you see it, changes how you understand every moment of your life, including the sensation you feel right now, sitting in that chair with the seat pressing against you. You think that is the Earth pulling you down. It is not. And by the time we are done, you will never feel it the same way again. But let me not get ahead of myself. Let me do something unfair first. Let me build the wrong idea up as high as it will go. Let me make you believe it. Let me make you comfortable. Because the wrong idea is gorgeous. It works spectacularly well. And the people who created it were not fools. They were among the sharpest minds that ever lived. So give them their due, sit with the wrong idea, love it for a moment, and then we will set it on fire. You pick up a rock. You hold it out at arm's length. You let go, it falls. Why? Because the Earth is massive. The rock is massive. There is a force between them, a force of attraction, pulling the rock toward the center of the Earth. Isaac Newton wrote this down in 1687 in one of the most important books ever published, the Principia Mathematica. The force of gravity between any two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them, multiplied by a universal constant we call big G. The force is always attractive. It pulls along the line connecting the two objects. It gets weaker with distance, but it never goes to zero. Every piece of matter in the universe pulls on every other piece of matter. That is Newton's law of universal gravitation, and the word universal is doing real work there. It is the same law for an apple falling off a tree, and for the moon swinging around the Earth, and for the Earth swinging around the sun, and for the sun orbiting the center of the Milky Way. One law, everywhere, always. Newton showed that the force making the apple fall and the force keeping the moon in orbit are the same force. That was one of the great unifications in the history of science. Two things that look completely different, falling and orbiting, turned out to be the same phenomenon seen at different scales. And the predictions. My God, the predictions. You can use Newton's law to calculate the orbit of the moon to extraordinary accuracy. You can aim a spacecraft at Jupiter and hit your target after traveling hundreds of millions of miles. Edmund Halley used Newton's law to predict that a comet he observed in 1682 would return roughly 76 years later in 1758. He died 17 years before the comet came back. But it came back right on schedule, and they named it after him. That is the power of a law that works. But here is maybe the most dramatic example. In the 1840s, a French mathematician named Urbain Le Verrier was studying the orbit of Uranus, and he noticed something was off. Uranus was not quite where Newton's law said it should be. It was being tugged by something. Leverrier sat down and calculated where an unknown planet would have to be to produce exactly the deviations he was seeing. He sent his prediction to an astronomer in Berlin. The astronomer pointed his telescope at the predicted location. And there it was. A brand new planet. Neptune. Discovered not by looking through a telescope, but by trusting Newton's math and solving an equation. That is power. That is a theory you can believe in. So you might say, what could possibly be wrong? If Newton's law discovers new planets, what more do you want from a theory? Fair question. And here is where the trouble starts. Newton himself knew something was deeply wrong. Not with the predictions, with the meaning. He wrote it in a letter to Richard Bentley, and I will paraphrase the idea that one body acts upon another at a distance, through a vacuum, with nothing in between to mediate the action, is to me so great an absurdity that I believe no one with a competent faculty of thinking could ever fall into it. Newton wrote that, the man who invented the theory. He was telling you, I can tell you what gravity does, but I cannot tell you what gravity is. I cannot tell you how the sun reaches across 93 million miles of empty space and grabs the Earth. There is no rope. No field, no mechanism, nothing, just action at a distance. And this action is instantaneous. In Newton's theory, if the sun suddenly doubled in mass, the Earth would feel the change right now. Not 8 minutes from now, which is how long light takes to cross that gap. Now, Immediately. Zero travel time. The gravitational effect crosses 93 million miles in no time at all. That should bother you. That should really bother you. Because it means the sun somehow knows right now, this instant, exactly where the Earth is and how far away it is and how much it weighs. And it adjusts its pull accordingly, in real time, faster than light, faster than anything. In Newton's day, this was uncomfortable but survivable. Nobody had a speed limit for information. But after Einstein published special relativity in 1905, establishing that nothing, no signal, no influence, no information of any kind, can travel faster than the speed of light, Newton's instantaneous gravity became more than uncomfortable. It became a contradiction, a serious one. But before we get to Einstein, let me hit you with something else. Something that bothered people even more than the action at a distance. A coincidence so strange, so precise, so unexplained, that it sat in the foundations of physics like a crack in a wall for over 2 centuries, and nobody could patch it. In Newton's physics, the word mass means 2 entirely different things, meaning number 1, inertial mass. This is the stubbornness of an object. How hard it resists being pushed. You shove a bowling ball, it barely moves. You shove a tennis ball with the same force, it flies across the room. The bowling ball has more inertial mass, more resistance to acceleration. This appears in Newton's second law. Force equals mass times acceleration. The mass in that equation, the one that determines how much the object resists your push, is inertial mass. This has nothing to do with gravity. Nothing at all. It is a property of matter's resistance to changes in motion. Meaning number 2, gravitational mass. This is how strongly an object participates in the gravitational interaction. How powerfully the Earth pulls on it. How powerfully it pulls back on the Earth. This appears in Newton's law of gravitation, a completely different equation, measured by a completely different experiment. Conceptually, it is a completely different property. So you have 2 numbers attached to every object. Inertial mass, how much it resists being pushed. Gravitational mass, how strongly it feels gravity. They are defined differently, they are measured differently. They live in different equations, and they are exactly equal every single time for every material ever tested. Gold, aluminum, granite, water, styrofoam, neutron star material, if you could get some. The ratio of gravitational mass to inertial mass is precisely 1 to better than 1 part in a trillion by the best measurements we have. Why? In Newton's framework, there is no reason. None. It is just a fact, an empirical accident. You measure both masses, you get the same number, you shrug, and you move on. Imagine if this happened in electricity. Imagine you discovered that the electrical charge of every object is exactly equal to its weight. Precisely. Every material, every shape, every temperature. Charge equals weight. You would say that is insane. That cannot be a coincidence. Something deep must connect charge and weight, some hidden unity we have not found yet. That is the situation with inertial and gravitational mass. 2 conceptually unrelated quantities. Perfectly equal. For everything. Always. And nobody could explain it. Galileo noticed the consequence centuries earlier. He showed, or at least argued compellingly, that all objects fall at the same rate regardless of their mass. Drop a cannonball and a musket ball from the same height. They hit the ground at the same time. This follows directly from the equality. The gravitational force is proportional to gravitational mass. The resistance to acceleration is proportional to inertial mass. If they are equal, they cancel out of the equation, and every object accelerates at the same rate. The falling rate depends only on the strength of the gravitational field, not on the object. Beautiful, mysterious, unexplained. For 250 years, nobody could crack it. Then one person sitting in a patent office in Bern, Switzerland, around 1907, refused to look away from this coincidence. He stared at it. He turned it over in his mind. He asked what the universe would have to be like for this coincidence to be not just true, but obvious. Inevitable. Trivially so. Albert Einstein called what happened next the happiest thought of his life. Here it is. I want you to picture this as vividly as you can. A man is standing in a box. A closed box with no windows. The box is sitting on the surface of the earth. He feels his weight. His feet press against the floor. He drops a ball and it falls. He pours a glass of water and the stream arcs downward. Everything is normal. Gravity as you have always known it. Now take that same man, put him in the same box, but this time the box is floating in deep space. No planet anywhere near. No star. No source of gravity for billions of miles. Empty void, but the box has a rocket strapped to its bottom, and the rocket is firing, accelerating the box upward at exactly 9.8 meters per second. The man inside feels his weight. His feet press against the floor. He drops a ball and it falls because the floor is accelerating upward into the ball, and from his perspective inside the box, the ball drops just the way it would on Earth. He pours water and the stream arcs downward. Everything is exactly the same. Can the man tell which box he is in? No, he cannot. Not by any experiment, not by any measurement, not by any trick. The two situations, sitting in a gravitational field and accelerating in empty space, are physically, operationally, fundamentally identical. This is the equivalence principle. And it is not an approximation. It is not a thought experiment meant to suggest a rough similarity. It is a statement about the architecture of reality. Gravity and acceleration are the same phenomenon. Now think about what this means for the ball in the accelerating box. There is no gravitational force in that box. The ball, when released, is not being pulled by anything. It is floating, at rest, at peace. The floor rushes up and hits it. The ball did nothing. The floor did everything. From the ball's perspective, it is in a state of zero force. Einstein said, that is what is happening on Earth. When you drop a ball, the ball is not being pulled down. The ball is doing the most natural thing in the universe. It is floating, coasting, following the path of zero force, the path of pure inertia, the path of maximum laziness. We call it free fall. And free fall is not falling at all. Free fall is the state of being utterly undisturbed. It is you standing on the ground who is not in a natural state. The atoms in the floor are pushing against the atoms in your shoes, and that electromagnetic push is accelerating you upward, away from the path you would naturally follow. You are being shoved constantly, every second of your life. The ground pushes you, the chair pushes you, the bed pushes you. You have never, since the moment you were born, except for brief moments in the air when you jump, experienced the natural state of zero force. The ball experiences it every time you let go. That is an astonishing reversal. In Newton, you are at rest, and the ball is being acted on. In Einstein, the ball is at rest, and you are being acted on. The whole picture is inverted, and the equivalence principle does not stop there. It makes predictions that Newton's theory never could. Think about the accelerating box again. Suppose someone outside the box shines a beam of light horizontally through a small window on one side. The light enters the box traveling horizontally, but the box is accelerating upward. By the time the light crosses to the far wall, the box has moved up a tiny bit. From inside the box, the light appears to curve downward. It bends. Now apply the equivalence principle. If you cannot distinguish between the accelerating box and a gravitational field, then light must also bend in a gravitational field. A beam of light passing near a massive object should curve toward it. Newton's gravity has no way to predict this because in Newton's picture, light has no mass and the gravitational force acts on mass. But in Einstein's picture, light follows geodesics just like everything else. It follows the straightest path through curved space-time. And if space-time is curved near the sun, the path of starlight passing close to the sun should bend. In 1919, Arthur Eddington led an expedition to the island of Principe off the west coast of Africa to observe a total solar eclipse. During the eclipse, with the sun's glare blocked by the moon, he photographed the stars near the edge of the sun and measured their apparent positions. They had shifted. The light from those stars had been deflected by the sun's gravity, exactly the amount Einstein's theory predicted, and roughly twice what a naive Newtonian calculation would give. The result was announced in London in November of 1919, and it made Einstein world famous overnight. The headlines were extraordinary. But the real significance was not fame. It was proof. Proof that space-time is curved. Proof that gravity is geometry. But you might reasonably object. You might say, fine, I accept that the person in the accelerating box feels like gravity. But on the surface of the Earth, nothing is accelerating. The ground is just sitting there. How can standing on stationary ground be acceleration? In flat space it could not be. You are right. But here is Einstein's great insight, the one that took him from 1907 to November of 1915 to fully work out. Space is not flat. time is not uniform. The presence of mass and energy curves the geometry of space and time itself, and in that curved geometry, standing still on the surface of a planet is not a state of rest. It is a state of acceleration. You are being pushed off your natural path, which would be freefall, by the rigidity of the ground beneath you, curved space-time. That phrase makes people nervous because it sounds like heavy mathematics. So let me show you what it looks like with no math at all. And two people stand on the equator of the Earth, one in Brazil, and one in Central Africa, 1,000 miles apart. They both face due north. They both begin walking in a perfectly straight line. No turning, no drifting, absolutely straight. Watch what happens. As they walk north, the distance between them shrinks. They converge. By the time they reach the North Pole, they are standing side by side. They started far apart, walked in parallel straight lines, and ended up in the same place. If you did not know the Earth was round, if you thought the surface was flat, you would be baffled. You would say something must be pulling them together, some force of attraction between walkers. You would write down a law. Walker gravity. The attractive force is proportional to their walking speeds and inversely proportional to the square of their separation. The law would work perfectly. It would predict the convergence exactly. But there is no force. There is no attraction. Both walkers walked straight. On a curved surface, straight lines converge. That is not physics. It is geometry. Pure, simple geometry. Einstein's claim is that this is precisely what gravity is. Both mass and energy warp the geometry of space and time. Objects in that warped geometry follow straight lines, the straightest possible paths through curved spacetime, which we call geodesics. And because the geometry is curved, those straight paths converge toward the mass. From the outside, it looks exactly like a force is pulling them. But there is no force. There is only the shape of the road. Now, you may have seen the popular picture of this. A heavy ball sitting on a stretched rubber sheet making a dip, and a marble rolling around the dip in a curve. That image is everywhere, and it is profoundly misleading, for two reasons. First, it only shows the warping of space, and I have already told you that the warping of time is the more important effect for everyday gravity. The rubber sheet has no way of showing you time flowing at different rates. It is a purely spatial picture of a phenomenon that is mostly temporal. Second, and this is the killer, the rubber sheet picture is circular. Why does the marble roll toward the heavy ball? Because of gravity. The demonstration uses the very thing it is trying to explain. In the real universe, there is no downward for space-time to dip into. The curvature is intrinsic. It exists within the four-dimensional fabric itself, without any need for an outside space to curve into. It is like the curvature of the Earth's surface. You can measure it from within the surface without ever leaving it, without ever needing a third dimension to curve into. But the rubber sheet cannot show you intrinsic curvature, so it cheats, and the cheat relies on the very force it claims to be explaining. Throw that picture away. It does more harm than good. The real picture is the two walkers on the sphere. No external force, no gravity in the demonstration, just geometry. Straight lines on a curved surface converge. That is it. That is the whole story. The moon orbiting the Earth is not being tugged by an invisible rope. The moon is coasting in free fall, following a geodesic through the curved spacetime around Earth. That geodesic happens to be a closed curve, what we see as an orbit. The moon feels no force. It is doing nothing. Spacetime is curved, and the moon is following the only straight path available. An apple falling from a tree is not being pulled downward. The apple is following a geodesic. In the curved spacetime near the Earth's surface, that geodesic leads toward the center of the Earth. The apple is in the most natural state possible. Zero force. You, standing under the tree, are the one being forced. Electromagnetic forces in the ground push upward on your feet, diverting you from your own geodesic. You are the disturbed one. The apple is free. I should tell you how this theory was tested. Not the 1919 eclipse, which I mentioned. Something even more dramatic, because it solved a mystery that had been tormenting astronomers for half a century. Remember how I said Leverrier used Newton's law to discover Neptune by tracking deviations in the orbit of Uranus? Well, Leverrier also noticed that the orbit of Mercury was misbehaving. Mercury's orbit is an ellipse, and the axis of that ellipse slowly rotates around the Sun, a phenomenon called precession. Most of the precession could be explained by the gravitational pulls of the other planets. using Newton's law. But when you accounted for all those pulls, there was a tiny leftover, 43 arcseconds per century, an incredibly small amount. But it was there, it was consistent, and Newton's theory could not explain it. Leverrier tried the same trick that had worked for Uranus. He proposed an undiscovered planet, Vulcan, orbiting closer to the Sun than Mercury, whose gravity would explain the extra precession. People looked for it. For decades they searched. They never found it. Because it was not there. When Einstein completed his field equation in November of 1915, one of the very first things he did was calculate the precession of Mercury. His equation, with no adjustable parameters, no fudge factors, no hidden planets, predicted an extra precession of exactly 43 arcseconds per century, exactly the observed value. Einstein later said that when he saw this result, his heart literally palpitated. He knew the theory was right. Now, here is a subtlety that almost every popular account gets wrong, and it is crucial. When people hear curved space-time, they picture warped space. They imagine space being dented or dimpled, like a bowling ball on a rubber sheet. You have seen that picture. It is on every science website, and it is misleading because in everyday situations near the surface of the Earth, the curvature of space is almost negligible. What does the real work is the curvature of time. Let me show you what I mean. Take two identical clocks, perfect atomic clocks, synchronized to the same tick. Place one on the ground floor of a building. Place the other on the roof, say 30 meters higher. Wait a day, come back. Compare the clocks. The clock on the ground floor has ticked fewer times. It has fallen behind, not because it malfunctioned, not because of vibrations or temperature differences, because time itself passes more slowly, closer to a massive object. The closer you are to the Earth's center, the slower your clock ticks. The higher you go, the faster. This is called gravitational time dilation, and it is not a thought experiment. It is a measured fact. Robert Pound and Glenn Rebka verified it at Harvard in 1959. They fired gamma-ray photons up a tower and measured the tiny shift in frequency caused by the difference in gravitational potential between the top and the bottom. The shift matched Einstein's prediction to high precision. Decades later, the same effect was confirmed with atomic clocks flown on airplanes, and with clocks at different altitudes in laboratories. Today, every satellite in the GPS constellation corrects for this effect. The satellites orbit about 20,000 kilometers up, where time runs slightly faster than on the surface. If the engineers ignored this correction, your GPS position would drift by roughly 10 kilometers per day. Within a week, the system would be useless. Now here is the profound part. This difference in the flow of time is the primary source of what we call gravitational acceleration, not the curvature of space, the curvature of time. Think of it this way. Everything is always moving through time. You are moving through time right now. Even if you stand perfectly still in space, you are racing through time at 1 second per second. In physics, we describe motion through space-time, not just space. And objects follow paths that maximize their own proper time, the time read on their own clock. This is the geodesic principle. In flat space-time, the path that maximizes your proper time is simple. Sit still. Do not move through space. All your motion goes into time, and you age as fast as possible. But now place that object near a massive body. Time runs slower near the mass. If the object sits still near the surface, it is stuck in the slow time zone, and its clock ticks slowly. It could accumulate more proper time by drifting toward a region where time runs faster, which is upward, but it cannot do that either, because the ground is in the way. The natural path, the geodesic, the one that balances these effects and maximizes the total proper time over the whole trajectory, turns out to be a curved path through space-time, a path that, when projected onto space alone, looks like the object is accelerating downward. That is falling. That is what falling actually is. Not a response to a force, not being pulled. It is an object following the path through curved space-time that ages it the most. And because time runs slower near the Earth, that path curves downward. Gravity is the curvature of time, and falling is the natural response to uneven time. Let me make this even more vivid, because I think people hear the words but do not feel the strangeness. You are about 6 feet tall, let us say. The bottoms of your feet are 6 feet closer to the center of the Earth than the top of your head. That means time is running slightly slower at your feet than at your head. Right now, the difference is incomprehensibly tiny, something like a few parts in 10 to the 16th. but it is there and it is real, and it has been measured with atomic clocks separated by as little as 1 foot. Now your body is extended. The top of you is in a slightly faster time zone than the bottom of you. Every atom in your body, left to its own devices, would like to follow a geodesic. But different atoms at different heights have slightly different geodesics because the curvature is different at different heights. The atoms at your feet want to drift along a slightly different path than the atoms at your head. If your body were not rigid, if your atoms were not bound together by electromagnetic forces, you would be gently pulled apart. Not violently, not noticeably, but the tendency would be there. This is what we call tidal forces. They are the stretching forces that arise from the variation in curvature from one place to another. Near the Earth, tidal forces are negligible. You do not feel your feet and head being tugged in different directions. But near a very dense object, a neutron star or a black hole, the curvature varies enormously over short distances, and the tidal forces become savage. If you fell toward a stellar mass black hole feet first, the curvature gradient between your feet and your head would stretch you like taffy. Your feet would be accelerating toward the center much faster than your head. The technical term for this, and I love that it has a technical term, is spaghettification. The black hole would turn you into a long, thin strand of matter, not because of a force pulling you inward, because of the difference in curvature between 2 points 6 feet apart. That is how real space-time curvature is. It is not a metaphor. It is not a mathematical abstraction. It is a physical thing that would kill you, gruesomely, if you got too close to a sufficiently dense mass. I want you to sit with that, because this is the real answer to the question, why does mass create gravity? Mass does not create a force. Mass warps the flow of time. And when time flows at different rates in different places, the natural motion of objects, their zero-force free-falling motion, curves toward the mass. That is gravity, not a force across space, a gradient in time. And the coincidence of inertial and gravitational mass? The mystery that sat in the foundations of physics for 250 years. It evaporates. In Einstein's picture, gravity is not a force applied to objects from outside. Gravity is the shape of the space-time those objects move through. There is no separate gravitational charge. There is no second kind of mass. There is just mass, and the geometry it produces and the geodesics that geometry determines. Inertial mass and gravitational mass were never two different things. We were staring at one phenomenon through two different windows and wondering why the views matched. Of course they matched. It was the same room. Now, you might rightly push back. You might say, you have told me what mass does. It curves space-time, especially time. Fine. But how? How does a lump of matter reach into the geometry of the universe and bend it? Einstein's answer is a precise mathematical equation published in November of 1915 after years of grueling work. It is called the Einstein field equation. I will not write it down. It takes serious mathematical training to even read the symbols. But I can tell you what it says in words. On one side, a mathematical object that encodes the curvature of space-time at every point. How bent it is, in what direction, in what way. On the other side, a mathematical object that encodes the distribution of energy, momentum, pressure, and stress. Everything that counts as stuff. The equation says the curvature over here equals the stuff over there, multiplied by some constants. Tell me how the stuff is arranged, and I will tell you the geometry. Tell me the geometry, and I will tell you how the stuff moves. This is a dramatic improvement over Newton. Newton said mass creates a force at a distance, instantly, with no mechanism. Einstein says mass curves the local geometry. That curvature propagates outward at the speed of light, and each object responds only to its local curvature. There is no action at a distance. Everything is local. The sun does not reach across the solar system to grab the Earth. The sun warps the space-time in its immediate neighborhood. That warping extends outward, traveling at the speed of light, and when it reaches the Earth's orbit, the Earth responds to the curvature it finds itself in. The Earth does not know about the sun. It knows its own local geometry. That is all it needs. This also solves the instantaneous action problem that plagued Newton. In Newton's universe, if the sun vanished, the Earth would immediately fly off in a straight line. In Einstein's universe, the Earth would not know the sun was gone for about 8 minutes. The curvature near the Earth would remain exactly what it was, because the disturbance, the change in the gravitational field, would have to propagate outward from the sun's location at the speed of light. For 8 minutes, the Earth would orbit normally. Then the ripple would arrive, the curvature would change, and the Earth's path would shift. These ripples in space-time curvature are real physical things. They carry energy, they stretch and compress space as they pass. We call them gravitational waves. Einstein predicted their existence in 1916, just months after publishing general relativity. But for decades there was genuine debate about whether they were physically real or just artifacts of the mathematical formalism. Could a ripple in space-time actually carry energy, move things, be detected? The first indirect evidence came in 1974. Russell Hulse and Joseph Taylor discovered a binary pulsar, two neutron stars orbiting each other extremely closely and rapidly. They tracked the orbit over years and found it was decaying. The two stars were spiraling inward, losing energy. And the rate of energy loss matched with remarkable precision the amount predicted to be carried away by gravitational wave emission. The waves were real, they carried energy, the Hulse-Taylor measurement earned a Nobel Prize. Then in September of 2015, 100 years after the field equation, the LIGO Observatory directly detected gravitational waves for the first time. The source was two black holes, each roughly 30 times the mass of the Sun, spiraling into each other more than 1 billion light-years away, merging in a catastrophic collision that briefly radiated more energy in gravitational waves than all the stars in the observable universe were radiating in light. The signal that reached Earth was absurdly faint. It stretched and squeezed LIGO's 4-kilometer detector arms by a length smaller than 1,000th the diameter of a proton, and they measured it. The waveform, the shape of the signal as it evolved over a fraction of a second, matched Einstein's prediction with breathtaking precision. That is the power of this theory. It predicted a phenomenon a full century before anyone had the technology to observe it. And when the observation finally came, the prediction was dead right. But I do not want to leave you thinking the story is over, because there is a deeper question lurking beneath everything I have said, and it is a question nobody on Earth can currently answer. I told you that mass and energy curve space-time. I told you Einstein's field equation relates curvature to the distribution of energy. Good, but why? Why does energy warp geometry? What is it about the presence of stuff that makes the fabric of space and time respond? And I have to be completely straight with you. We do not know. Einstein's equation relates two things, the shape of space-time on one side and the content of space-time on the other. It says they are proportional. But it does not explain the relationship. In the same way that Newton's second law, force equals mass times acceleration, relates force to acceleration without explaining why forces cause acceleration. At some level, every physical law is a description of what happens, not an explanation of why. You can always ask one more why, and at the bottom of the chain there is a brute fact that we accept because it matches experiment. That is how physics works, always has. But we have clues, and they are wild. First clue. In general relativity, space-time is not a passive backdrop. It is not the stage on which physics plays out. It is an active participant. It has energy. It has properties. It responds to matter, and matter responds to it. This is a fundamental shift from Newton, where space was an empty, rigid, inert container. In Einstein's universe, the container is alive. Second clue. The equation responds to all forms of energy, not just mass. Heat curves space-time, light curves space-time, pressure curves space-time. Even the gravitational field's own energy curves space-time. This tells you that what we call mass-creating gravity is really energy-creating curvature. And mass itself is a form of energy. Einstein's most famous equation, E equals mc squared, is the conversion formula. A kilogram of matter is a fantastically concentrated reservoir of energy. And in ordinary matter, the mass of a proton, for example, comes overwhelmingly not from the quarks inside it, which are nearly massless, but from the kinetic energy and field energy of the strong nuclear force binding those quarks together. Mass is energy. Energy curves space-time. That is the fundamental relationship. Third clue, and this one is stranger. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have thermodynamic properties. They have temperature, they have entropy. And the entropy, the amount of hidden information, is proportional not to the volume of the black hole, but to the area of its event horizon, its surface. This is deeply weird. Normal objects store information in their volume. A book twice as thick holds twice as much text. But black holes store information on their surface. This led to the holographic principle, the idea that all the information about a region of space-time can be encoded on its boundary. What does this have to do with gravity? Maybe everything. If spacetime's informational content lives on surfaces rather than in volumes, then spacetime itself might not be fundamental. It might be emergent. It might arise from something more basic, something involving quantum information, quantum entanglement, something we do not have a name for yet. Some theorists, like Ted Jacobson and Eric Verlinde, have pushed this further, arguing that gravity itself might be an entropic force. Not a fundamental interaction, but a statistical tendency, like the way a stretched rubber band pulls back to its relaxed state. Not because of a fundamental rubber band force, but because there are more microscopic configurations where the band is unstretched than stretched. The system drifts toward higher entropy. Could gravity be the same kind of thing? Could space-time curvature be a macroscopic average over some enormous number of microscopic quantum degrees of freedom, the way temperature is a macroscopic average over the motion of atoms? Nobody knows. The math is suggestive but incomplete. The ideas are beautiful but unproven. This is the frontier. This is where the sharpest minds in physics are working right now. And it is one of the greatest open questions in science. How does a quantum theory of gravity work? What is space-time made of? Why does energy curve it? I will tell you what I think is the deepest part of this mystery. Every other fundamental interaction in physics, electromagnetism, the strong nuclear force, the weak nuclear force, we understand at the quantum level. We have quantum field theories for all of them. Particles exchange other particles. An electron repels another electron by exchanging a photon. A quark attracts another quark by exchanging a gluon. The interactions are mediated by quantum fields described by equations we can calculate with. Gravity is the holdout. We do not have a working quantum theory of gravity. General relativity is a classical theory. It treats space-time as a smooth, continuous fabric. But we know from quantum mechanics that at the very smallest scales, the Planck scale, about 10 to the minus 35 meters, the smooth fabric picture probably breaks down. Space-time might become foamy, fluctuating, uncertain. Something quantum happens at that scale, and we do not know what it is. When you try to combine general relativity with quantum mechanics using the same techniques that work for the other forces, you get nonsense. Infinities that cannot be controlled. Predictions that are meaningless. The two greatest theories of the 20th century, general relativity and quantum mechanics, each spectacularly successful in its own domain, refuse to be combined. They are like two puzzle pieces from different boxes. Each piece is beautiful. They do not fit together. String theory is one attempt to make them fit. Loop quantum gravity is another. There are others. None of them is complete. None of them has made a prediction that we can currently test. The energy scales where quantum gravity effects become important are so fantastically high, so far beyond our technology, that direct experimental tests may be decades or centuries away. Or we might get lucky and find an indirect signature. Nobody can say. But this is not a reason for despair. It is a reason for excitement. Let me bring it all back together now. We started with the simplest sentence in physics. Mass creates gravity. 5 words, everyone knows them. And we pulled on that thread gently at first, then harder, and the whole tapestry came apart and reassembled into something unrecognizable. Mass does not create a force. Mass creates curvature. Curvature of space and, more importantly, of time. Objects are not pulled toward mass. They follow geodesics, straight paths through curved spacetime, paths that curve toward the mass because time runs slower there. Freefall is the natural state of zero force. Standing on the ground is the accelerated state. The equality of inertial mass and gravitational mass is not a cosmic coincidence, but a trivial consequence of the fact that gravity is geometry. Gravitational waves ripple through the universe at the speed of light, carrying energy, confirming that spacetime is a dynamical physical entity. And beneath all of this, there is a question that no human being can currently answer. Why does the presence of energy warp the fabric of reality? That is physics. Start with a question so simple a 5-year-old could ask it. Why do things fall? Follow it honestly, without turning away when it gets uncomfortable, and it carries you to the very edge of what our species knows. And when you get to that edge and look over, the question is still there. Deeper, more beautiful, unanswered. That is not a failure. That is the whole point. That is the thing that makes this worth a life. I want to say one more thing because it is important and people get it wrong. They hear Einstein was right and Newton was wrong and they think, good, we threw out the old theory and replaced it with the correct one. But that is not how physics works. Newton was not wrong. Newton was incomplete. in the same way that a flat map of your neighborhood is not wrong. It shows you the streets. It tells you how far the store is. It works perfectly for navigating your town. It only fails when you zoom out far enough for the curvature of the Earth to become significant. Then you need a globe instead of a flat sheet. Newton's gravity is the flat map. It works for everything humans encounter in daily life. It works for engineering. It works for space travel. It launched every rocket and aimed every satellite. It is a magnificent theory, but it is a local approximation to a deeper truth. Einstein's gravity is the globe. You need it when the curvature matters. Near black holes, for the precision timing of GPS satellites, for understanding the expansion of the universe, for knowing what gravity actually is. And here is the thing. Einstein's theory will someday be found incomplete too. There will be situations almost certainly involving the quantum behavior of gravity at extremely small scales, where Einstein's predictions break down, and someone will build a deeper theory that contains Einstein's the way Einstein's contains Newton's. Layer after layer, each one valid in its domain, each one transcended at the boundaries. That is not a depressing thought. It is the most hopeful thing I know about science. We are never done. There is always another layer. There is always a deeper question. So, the next time someone asks you, why do things fall? I want you to resist the easy answer. Do not say because of gravity. That is circular. You are explaining falling by invoking a word that means the tendency to fall. You have said nothing. Do not say because mass creates a force. That is Newton, and it is incomplete. It describes what happens, but not what is really going on. Say this instead. Things fall because the presence of mass and energy warps the fabric of space and time, and in that warped geometry, the natural path of any object, the path it follows when absolutely nothing is acting on it, curves toward the source of the warping. Things fall because that is what going straight looks like when the road itself is bent. And if they stare at you blankly, which they will, smile and say, "That took the greatest minds in human history about 250 years to figure out. Give yourself a minute." I will leave you with this. You are sitting or standing right now. You feel weight, pressure. Your whole life you have been told that what you feel is the earth pulling you toward it, the force of gravity acting on your body, pulling you down. But now you know something different. What you feel is the ground pushing you up, the floor or the chair exerting an electromagnetic force against the soles of your feet or the back of your legs, shoving you upward away from the geodesic you would naturally follow. If the floor disappeared, you would not fall, you would be liberated. You would float along the straightest possible path through the curved space-time around Earth, and you would feel nothing at all. No weight, no pressure, no force, complete weightlessness. The purest state of physical freedom. The Earth is not pulling you down. The ground is pushing you up. Those two sentences sound almost the same, but the gap between them is 250 years of physics. It is the gap between Newton and Einstein, between a description and an understanding, between knowing the name of a thing and knowing what the thing actually is. Stand up, feel your feet against the floor, close your eyes for a moment, and ask yourself honestly for the first time, which one of us is really being pushed around? Me or the falling apple?